So welcome all to this month's webinar. We're talking about hydrocarbons, VOCs, and all related to the waterproofing design of structures. But we know that designing and working below the surface of the ground involves not just understanding the geology and the hydrology of the materials, but we have to appreciate that designers need to understand that there are other substances within the ground, and it's important to recognize that so in order to mitigate those hazards. So we're talking principally here on VOCs, but we're talking, how many VOCs are there? Well, it's estimated that there are thousands of these volatile compounds, but there's no test for all of them. So we need to understand what we're dealing with. So as we said, this month's presentation is talking about hydrocarbons and VOCs in the waterproofing industry. So we've got Steve Wilson with us from EGDP, and he's going to give this presentation. So what I'd like to do now is just hand the camera over to Steve and leave the presentation to you. Please take it away, Steve.
All right. Thank you very much, and thank you to the PCA for inviting me to give this presentation. So it's about hydrocarbons, VOCs, and waterproofing design, and some of the important considerations that you need to think about. So the aims of today are to highlight the differences between methane and carbon dioxide and volatile organic compounds. So volatile organic compounds, I'll refer to them as VOCs. I'll explain what experience and skills are necessary for VOC mitigation design. Then look at the risk assessment process for the design and specification of VOC membranes. And there are case studies of good and bad practice throughout the presentation. So a few years ago, there was Dave Cook's blog on the PCA website, who really, the inimitable Mr. Cook, when it does come to VOCs, what he was saying is correct. You need to know your limitations, because they are different to methane and carbon dioxide, and they aren't simple things to deal with. Even qualified risk assessment professionals sometimes have difficulty doing VOC risk assessments, and I'll explain some of the reasons why that is during the presentation. So I do see a lack of competence in where waterproofing advisors are providing advice on VOC mitigation systems, and these are some statements that I've seen being made. So the membrane has been tested in line with the 9 standard challenge chemicals. What that's referring to is C748, and then on the basis of those test results, it's summarized as an excellent barrier, and that those 9 challenge chemicals are representative of the performance against all ground conditions with VOC contamination. That answer, it just demonstrates poor understanding of VOC membranes and risk assessment. So there are over 10,000 VOCs, and we do not test or risk assess for all of them. Some of them don't even have sort of limits that you can design against, because the toxicologists haven't done the necessary research. The good thing is that the reviewer is asking for a risk assessment, but the answers are quite worrying, because nowhere in any of the guidance documents does it define or refer to an excellent barrier. And you can't do that, because VOC membranes are permeable to VOCs. They don't stop the flow completely. And for that reason, when you're designing the VOC membranes or the system, a risk assessment is required, and it needs to be site specific for the contaminants that are present on your site, with permeation data for the contaminants of concern. And sometimes we've been involved in sites where we specifically have to ask manufacturers, or we do the testing ourselves on a specific membrane, because the data isn't there, because we've found a VOC that is not one of the more common ones. So there are significant consequences where if you don't understand the VOC risk and you provide poor advice, then there are consequences. And the first of those is that it can cost clients a lot of money by specifying VOC membranes when they're not required. But more importantly, people don't recognise high-risk situations and end up specifying inadequate protection that puts the health of occupiers at risk and results in costly remedial works. And that's not just across waterproofing professionals, it also extends into the contaminated land industry as well. So you can see on the right-hand side there, we're coring through a concrete floor in an occupied building because VOCs are entering that building and building up at concentrations that are unacceptable, that are a hazard to health. And the mitigation design below that slab wasn't sufficient for the concentrations of hydrocarbons or VOCs that were in the ground. And that cost, just the investigations to determine what the problem was and then determine a design solution was expensive, and then installing the design solution was expensive as well. So it cost the contractor a lot of money. We're talking tens of thousands of pounds to put that right. So if we go back to the beginning, where do we find VOCs? So they're in the ground below old industrial sites, below petrol stations, below dry cleaners, anywhere where, for example, petrol, diesel or oil has been stored, either below or above ground. So some of the more common ones are benzene and toluene, which are present in petrol and diesel, so they're known as petroleum hydrocarbons. But you can also find them anywhere where cleaning or degreasing has been undertaken, and there you'll commonly find things called chlorinated solvents. And it's not just in tanks. Drum storage and spillage can cause significant ground contamination over many years. And so quite often you will see areas like this, particularly in poorly managed older sites. And there was actually quite a famous case where just spillage of a chlorinated solvent at a tannery site over the years, when they were transferring it from drums into other containers, had contaminated the groundwater in Cambridgeshire and resulted in quite a costly legal claim against the owners of the site. So the difference in risk between methane / carbon dioxide and VOCs. On the left-hand side, we've got methane / carbon dioxide. And typically you have hundreds of thousands of milligrams per metre cubed as a source concentration. So the methane and carbon dioxide are present in percentage concentrations in the ground. The migration rate through a gas membrane is actually very low. I can't see the actual number there, but it's 4 times 10 to the minus 6, I think, milligrams per metre cubed per hour. But the target concentration inside the building, even if we use a minimal risk value of 100 ppm methane, that is still very high compared to the rate at which the gas can migrate through the membrane. So in effect, on the left-hand side, providing the membrane is installed correctly, the membrane does effectively create a barrier to gas migration. But that's not the case on the right-hand side, where you've got hydrocarbons. So in this case, we have got much lower source concentrations of vapour in the ground, but the permeation rate through the membrane is much, much higher. So you can see there, that's just an example that toluene through HDPE, a typical permeation rate would be 23,000 milligrams per metre squared per hour, which is high when you compare it to the target concentration, which is tens of micrograms per metre cubed. So a microgram is a part per million. So it's very low. And so the VOC membrane doesn't create a complete barrier to VOC migration into buildings. And on some sites, not all, but some sites, there will be situations where just putting a membrane in is not sufficient. And that's where you've got high concentrations very close to the underside of the membrane, or of particular relevance in this context is where you've got basements in groundwater that is contaminated with VOCs. So if you don't take anything home at all from this presentation except one thing, it's there in red at the bottom. There is a limit to what VOC membranes can do. They are not a complete barrier to migration. Another way of looking at it, if we look at the right-hand side, first of all, so that's where we've got methane in the ground. And if you've got a negative pressure inside a building, which you would typically have, there's typically a negative pressure inside a building of a few pascals. And if you want to suck the methane out of the soil gas from the underside of that slab sufficiently to create an explosive atmosphere, i.e. to meet the lower explosive limit of methane at 5%, you would have to suck the soil gas out from 128 metres cubed of soil to achieve that. And that's effectively over the full footprint of a building, which is typically, that's a typical house dimension there. But you'd have to suck it out down to 2 metres. And that can't happen. It's in most soils, unless you've got an open pathway like a mine shaft, in most soils there's a head loss, so the pressure bulb below any cracks in the floor slab only extends 300 or 400 millimeters below the slab, so it's a physical impossibility. But on the left-hand side with the VOCs, again, this is TCE, which is one of the dry cleaning materials. It's a common VOC on laundries. And the reference concentration, the allowable concentration inside the building, is 2 micrograms per meter cubed. And if you've got a particularly dirty site where you've got high soil vapor concentrations, you only need to suck the soil gas out from 0.26 meters squared of soil, which is about 4 millimeters depth in that situation there. I can't remember what the radius, what radius I've allowed, but it's very, very small, and so it's feasible, and it does happen. And that is why VOCs are at much more of a risk than methane and carbon dioxide. You only need small volumes of VOCs to exceed the acceptable limits inside a building. So, are all hydrocarbons VOCs? No. So hydrocarbons are compounds of hydrogen and carbon joined together. And so one of the principal ones are the chief components that are of petroleum and natural gas. But VOCs are any organic chemical compound that can significantly vaporize under conditions of normal atmospheric temperature and pressure. So hydrocarbons, for example, include oil. And oil on its own is not a VOC. There might be VOCs within it, but it's predominantly heavy end, what we call heavy end hydrocarbons, which don't volatilize. So in simple terms, that means that it's compounds that are likely to change into gases. So compared to compounds like water, they evaporate with far greater ease, and that means they can quickly contaminate indoor air. And if they're present in water, they can diffuse into concrete, through concrete and into basements. And there are various limits that people apply to define what a VOC is. So one in BS 85876 is that it's a liquid at 20 degrees C and a boiling point less than 180 degrees C. An EU definition is that it's got a vapor pressure less than 0.01 kPa. But ultimately, it means that they produce gases or vapors at normal temperature and pressure. So membranes or any VOC protection system is required to prevent ingress of VOCs, but not all hydrocarbons. So there are many hydrocarbons that aren't volatile. And in chemistry terms, if you look on the right-hand side, that's a molecular sort of diagram of benzene. So it's got 6 carbon atoms that are joined together in a ring, and then each carbon atom has a hydrogen atom attached to it. And so because it's got 6 carbon atoms, we refer to that as the carbon chain length. So hydrocarbons with carbon chain lengths greater than 16 are not volatile. So you can see on that table on the right hand side, if you look at things like petroleum, jet fuel, kerosene, they're predominantly less than C16, and so they will volatilize very easily, and the compounds within them, the individual compounds, will volatilize. Diesel sits sort of mid-range. Some of it will volatilize, other parts of it won't. And then if you look at motor oil, there aren't any VOCs in motor oil. So only contaminants that are sufficiently volatile pose a vapor intrusion risk. And I suppose if you, in simple terms, the blacker and stickier the material is, the less likely it is to be volatile. One of the important things is that most polycyclic aromatic hydrocarbons, which are referred to as PAHs, are not volatile. So we quite frequently see references to PAH and then recommendations that it needs a hydrocarbon membrane. Well, in the vast majority of cases, it won't. There are a couple, such as naphthalene, that are volatile to an extent, but it's rare that that is a risk driver on a site. So just before we go on a bit more detail about VOCs, you do need to think about other compounds and gases that have similar issues. So there are semi-volatile organic compounds, which include some pesticides, some plasticizers, some fire retardants that can be contaminants in the ground that you might have to look at in terms of providing protection against. Elemental mercury is a particularly nasty material if it gets below a building or if it's present on a site, because the allowable concentration is 30 nanograms. I don't know what that is in terms of sort of parts per, but it's extremely small. And we had to look at a site to remediate a site where there was mercury contamination, simply from somebody dropping a barometer and breaking the mercury in the barometer. And it went through the wooden floorboards below a house and soaked into the soil. And it took us a long time. We excavated a lot of the soil and removed it. But even then, there was still residual mercury. You can see on the right-hand side, that's the gas monitoring that we did. So on the bottom there, you can see the mercury vapor and the way it's influenced by the heating system. When there's a fan on and fan off, it took us a lot of work to make sure that that was safe for people to live in it. And then also just things like hydrogen sulfide, which is more likely to cause an odour risk, an odour nuisance before it becomes a health risk. So on to VOC membrane design, and I think it's important to differentiate between design and detailing. And I'm I've got a degree in civil and structural engineering, and I have done structural design work in the dim and distant past. So I compare it to structural steelwork. And the design of structural steelwork is the structural analysis and specification of the steel beams and columns. And detailing is drawing up all the connection details, etc., and drawing it up onto drawings so that somebody can construct it. So comparable sort of things in VOC design. The VOC design is the risk assessment process to determine the required properties of the membrane and what other elements of protection are necessary. And then detailing is the drawing of site and building specific details to incorporate the membrane into the basement construction. And it's important here to make clear that supplier standard details are not adequate, as in not sufficient for a detailed design. They can inform a detailed design, but they are not the detailed design. And the construction process must be considered. So can the line that you are putting on the drawing be installed within the construction process for the structure? And when does it need to be installed? Now, personally, I would say that the waterproofing designers are very good at detailing. They understand the construction processes, but I don't think that if there's anybody, they may, or very few, that have the sufficient skills and background to actually do the risk assessment process, because it's a contaminated land consultancy skill that is required there. So if you are doing it, you probably need to bring in the necessary skills to do that. And durability, another important consideration on this is durability is different to permeation when you're looking at membranes. So if you're looking at durability, then that needs to be assessed when the membrane is in contact with any hydrocarbon, not just VOCs, because the hydrocarbons can attack the membrane material. So that's an important thing when you come to membranes that are below the water table, where they're in contact with the contaminants. So this is risk assessment, and these are the most difficult bits of risk assessment. So if you look at this, essentially what I'm showing you there, the tables, you've got a lot of information and different test data that people have done to look at what the concentrations of contaminants are below that site. So you've got soil concentrations, you've got PID results, which are just a screening measure of total hydrocarbons in the gas monitoring wells. You've got data from groundwater, so groundwater concentrations, and you've got soil vapor concentration, so the concentration of vapor above the groundwater table. And then if you look on the right hand side, I've already simplified what the ground model is, but you've got to create that simplified ground model from borehole records, trial pit records, the information that's being provided, groundwater monitoring, etc. And then you impose the building on that. So that is a conceptual model. And any hydrocarbon risk assessment should include a visual conceptual model such as that. And that in itself can be quite difficult to create because you're trying to simplify down quite complicated information. So you can see here you've got local pockets of soil contamination below the immediately below the basement floor slab. You've got perched water because you've got layers of more clay material in a sandy material, and then you've got a deeper groundwater table, and you've got different locations where hydrocarbons have occurred, so on the perched water and below there in the main groundwater table. So to design, to do a VOC risk assessment, that requires modelling. You've got to model how fast the VOCs are going to get into that basement. So you've then got to simplify that into something that you can analyse, to something like this. So then you need another diagram to explain which equations you are using to analyse the different parts of the process. So you've got the source of the hydrocarbon vapor. You've then got to calculate how that source transfers into a soil vapor concentration. You've then got to calculate how fast it moves through the soil, through the concrete, and then the dilution inside the building. So it's quite a complicated process. And there are different equations for different situations. You've really got to draw a conceptual model for the calculations as well. So the design of a VOC membrane should extend the risk assessment that has been done originally that says there is a risk, to show that the mitigation that is proposed reduces that risk to an acceptable level. And it uses models or equations to estimate permeation into the building, as I've just shown you. But it's not just putting numbers into equations. Doing the sums is the easy bit. Yeah, I could do the sums in 2 minutes. Yeah, just bung everything into a spreadsheet, job done. The time and effort is in making sure that you put the right numbers into the right equations. And all models are wrong, but sometimes some are useful. The numbers are there to help you make a judgment on whether it's acceptable. They are not the answer in themselves. And that is a fundamental principle of risk assessment. So if you look at what you have to do on the right-hand side, you've got to collect the right data. You've got to critically assess the data quality to make sure that there aren't, somebody's not done something like measure gas in a flooded in a flooded monitoring well, for example, or they've put it in a place where they've missed completely the source of the gas or the VOC. You've then got to develop the visual CSM and define what is to be modelled, as I've just explained. Develop the model, i.e. write your own equations or choose an appropriate off-the-shelf one that is suitable for your site and building. Then choose the right numbers to put into the equations, and then run the model calculations. And you can see it's all those first parts are the things that take the time. And they could easily take 2 weeks to do that. And as I said, it's a couple of minutes to run the actual calculations. But after you've run the calculations, you then need to sense check the results against other lines of evidence. The calculations, as I said before, and I can't emphasize this enough, are an aid to judgment. They are not the answer. So the other thing is that a cocktail of contaminants might be present. So there are unusual ones that you will frequently come across in actual fact that aren't in Syria C748. So trialmethylbenzene is a common one on sites, and cis-123-DCE is also common, but they're not listed in C748. So you might have to ask a membrane supplier to give you the data for those materials, or you might have to actually spend some money as a designer, depending on how far in advance of construction you are, and get some materials and test it yourself. You also need to consider the combined effects. So we'd run the calculations for individual compounds, but there are synergistic effects. So benzene on its own will have a lower risk than if you combine benzene with the risk from other compounds. And so what you do, you look at things called hazard quotients, which is what that table is showing you on the right-hand side. And effectively, you've got to have a hazard quotient or a hazard index less than 1, and you can see there on the right-hand side that for all those groups of compounds, in the car park, the lift, and the apartment, there is a significant hazard index that's greater than 1, and it needs some serious remediation. Also, you need to think about the basement construction can increase the concentration of certain contaminants, and I'll talk about that in a minute when I talk about oxidation of hydrocarbons. Chlorinated solvents also degrade, and when they degrade, they produce other toxic compounds that may be more toxic than the original compound. It's known as dechlorination. So, for example, if you've got TC and DC, then the likelihood is that when it degrades, it will produce vinyl chloride in the ground. So you've got to understand the degradation processes and what it can produce. And there's a limit to what membranes can do and how much can be left in the ground. It's worrying that people in contaminated land world are saying that they're going to break the vapor intrusion pathway. So they're going to break the ingress into the building, and then they can leave as much dirt in the ground as they want to, and that is not an acceptable approach. So which model for basements? It depends where the groundwater is and what your building construction is. So the right hand side, figure 4.7 from NHBC Foundation NF94, hazardous ground gas, an essential guide for house builders. And this was written for methane and carbon dioxide essentially, but the same principles apply to VOCs. If the basement is below groundwater, the model will need to assess dissolved phase diffusion towards and through the membrane and any other construction that is there. And if it's in contact with dissolved phase contaminants, that can increase the diffusion rates through a membrane by a factor of 2. So you need test data where the VOC permeation rate is being measured when the membrane is in contact with a liquid, not when it's been in contact with a vapour. You also need to consider whether things called light non-aqueous phase liquids or dense non-aqueous phase liquids are present. So what that means is that's the actual hydrocarbon itself is there as a discrete layer, either on top of the water when it's light, so it's less dense than water, so it floats on the surface, or it's denser than water when it sinks to the bottom. So, for example, it will sink through gravel, and then if it comes up against a clay layer, it will sit in depressions in the clay layer. But that increases the risk of vapor intrusion significantly. And also it's a durability risk if it's in contact with the membranes. So it's really important to look and see whether there's any evidence of those things being present, which you can see in the chemical test data. So if you look on the right hand side, if we've got a basement above the water, where the water table is permanently below the bottom of the basement, gas phase flow is a critical factor, and you can model it using some of the standard VOC models that are around. If the water table is above the basement, then you obviously haven't got vapor phase flow, you haven't got gas flow. So you need to look at diffusion from the groundwater into the basement construction. And if it's a variable water table, then you've got to do both and see which gives you the worst answer. And if you use the wrong model, it can have significant implications. So on the right hand side is a job we were looking at, which was a high-rise building, big reinforced concrete floor slabs, so no ventilated void underneath it. It's a piled structure, and it's got big thick coil caps that extend into contaminated groundwater. The site had been dewatered to allow construction of the pile caps, but when we looked at the data, we realised that once the dewatering stopped, the groundwater would recover. There was contamination in the groundwater, and there was also free product, napple, floating on top of the water that would be in contact potentially with the concrete of the pile cap. Now we modelled benzene as a single parameter because we were in a rush on this job because it was during construction, but we assessed the results with the recognition that other VOCs were being present, and so we took into account that synergistic combined effect on the overall hazard quotient. And what that showed us was there was a risk of unacceptable VOC intrusion, and that vapour protection was necessary, and we specified a number of levels of protection to give an adequate factor of safety on that site. Then somebody came along who the client didn't like it because it would cost them money, and so they went shopping around to find somebody who would tell them what they wanted to hear. And somebody else did a model which they pulled up a published paper for a research paper and just copied the equations, the whole scale from that paper, even the same parameters in some cases, into the equations they were using for the site, and said, yeah, it doesn't need any VOC protection. But there were some quite crucial differences. One, we were looking at particularly risky areas in the lift stair cores because they have high negative pressures and they allow vapours to migrate higher in the building. whereas this alternative used an equation that was for a low-rise house. They assumed there was a floor slab with a clear ventilated void below it, which is clearly not the case, and they assumed that vapour diffusion was through the unsaturated zone, i.e. above the groundwater table, which is clearly not the key issue on the right-hand side. And so they effectively were telling the client that it didn't need VOC protection, but on the basis of a completely inappropriate model. So when do you need a VOC membrane? So the decision's based on risk assessment. As I said, you don't need a VOC membrane if there are only non-volatile hydrocarbons present that aren't in contact with the membrane. Some petroleum hydrocarbons, they may be present, but they biodegrade within the unsaturated zone. And so if you've got a significant unsaturated zone that's oxygenated below the slab, then if it's petroleum hydrocarbons only, there may not actually be any risk. The real risk is with chlorinated solvents, because that doesn't apply to chlorinated solvents. They don't biodegrade in that unsaturated zone. So, but if you're putting a basement in, what you need to be sure of is that by installing the basement, that you don't reduce oxygen ingress. So you might see an unsaturated zone when you're doing the site investigation. You might see an oxygenated zone in the gas monitoring. But when you install the basement, it stops oxygen flowing through the surface. And so it reduces that potential and reduces the factor of safety. Other things on the right-hand side there, the site we looked at, the membrane wasn't required because the basement excavation removed all the contamination that was posing the risk. So again, you've got to look at it on a site-specific basis. Membrane properties are key to the design, and particularly the permeation rates, as I've already said, of the different VOCs through different membranes. And it's important that you interrogate manufacturers or supplier specifications, because we've had issues on jobs we've looked at with data sheets, and this includes our clients, that we do a lot of work for. So we've seen incorrect conversion of units from lab test reports onto data sheets. We've seen materials tested that don't achieve breakthrough of the VOCs. So if you look on the right-hand side, that's testing on a membrane. So the top line on the graph is for toluene. And you can see that as you run a test, the rate at which the toluene passes through the membrane increases. So you need to get what is known as full breakthrough. So as it permeates into the membrane stores some of the VOC initially, and you need to overcome that so you're getting full flow through the membrane. So you can see there that the testing on that one took about 44 days to get a representative value for the toluene permeation. So if you've got tests that are only 2 or 3 days, it might be long enough if it's a really, really, really good membrane. But I would question any test data that's only 2 or 3 days, and double check it. Other issues we've seen is materials being delivered to site that are thinner than quoted on the data sheets. Again, if you're doing risk assessments, the thickness of the membrane is quite an important parameter in the calculations. If you've assumed a thickness and then the materials are being delivered are thinner, that can be significant. So really you should check on site. Part of the verification should be that the material thickness is measured on site. And you need to distinguish between what is critical for the VOC design and what is actually just marketing. The permeation rates and thickness, strength and puncture resistance, that's what you need to be looking at, not the blurb that surrounds it. And as a designer, you ask for the laboratory test reports to see those, or you do your own testing, as I said. You should sense check any data. Is the quoted permeation rate consistent with other test data for that material? There's a lot of published information, for example, on benzene and toluene permeation through HDPE. So if somebody gives you a test result for that is significantly different to those values, you should ask yourself why. And good suppliers shouldn't have a problem giving you the lab test reports. It's no different to asking for concrete cube tests. And importantly, as the designer, you have a duty to make sure that the data you are using is acceptable and representative. And I was at a conference last year when I asked a lawyer about this, and he said, absolutely, that is the case. If you don't do that, then you could be open to liability and claims. So the top set of results on the right-hand side, again, are a data sheet from a BBA certificate for a product. That doesn't mean because it's got a BBA certificate, it will work on your site. You need to check, and it says in the BBA certificate that you need to check that the product will actually work where you want to put it. Now we've seen these test results. It's for GP Titan Flex. We've got the test lab reports, and we know their correct values on the sheet. But I've also seen a data sheet that just replicates those numbers and puts a less than sign in front of them for another membrane. And even with the same membrane results, I have never ever seen two tests give identical results. So again, it may be that it's been tested and all the results are less than what are on this sheet. But equally, you need to ask the question and make sure that it has got the permeation rates that are being claimed. So we've talked about all that. So finally, when is a VOC membrane not enough? And you'd be surprised how many cases that applies. So this is just one example where localized areas of NAPL, the non-aqueous phase liquids, so the free material, are present outside a basement. And the risk assessment showed a high risk associated with vapor intrusion. And we had to consider vapor intrusion via various pathways through the water, through the unsaturated zone if the water level dropped, through the different materials, the concrete, the diaphragm wall there, and the waterproof concrete liner wall. And we also had to consider the lift pits as a high risk area because they carry VOCs to higher levels in the building. And in the end, on that site, the mitigation comprised a waterproof concrete basement structure with specific water bars to address the VOC issues. We then had a VOC membrane which was pre-applied and welded, but because of the presence of the NAPL and the high concentrations of the VOCs that were in the water, we provided an additional activated bentonite membrane, so a GCL. But the bentonite's been modified so that it absorbs VOCs or hydrocarbons. And the reason we put that in there was to minimise the exposure of the main VOC membrane and to minimise any risk of durability problems because of the extent of the contamination in the ground. And then we specified minimal internal ventilation rates that needed to be achieved as well. That was as a backup. It was to give us sort of increased comfort that everything would be okay. So, it's not just stick a membrane in and everything will be okay. And I've seen similar sites where we've been brought in very late in the day. We've not actually been able to solve problems for people because it's been too late. And the amount of mitigation that is required. To be honest, they walked away from us, so I don't know what they ended up doing. And then drain cavities and VOCs, another issue with waterproofing, that drain cavities allow dissolved phase VOCs into the building envelope. So you've got to look at what the concentrations are and what the consequences are of allowing the VOCs to drain into the cavities. And in some cases that will require a suitable membrane between the cavity drain and the occupied space. which again will be based on quantitative risk assessment and permeation rates through the cavity drain material and through any membrane that you provide. Other considerations are that if you've got contaminated water coming into that system, then you can't discharge that water to sewers or soakaways. The same applies actually to external drains as well. If you've got if part of your waterproofing system is an external drainage system, and the discharge, if you do discharge it, if you are allowed to discharge it, you actually need a permit from the Water Authority, which is explained in Surrey C795. And any discharge without a permit is illegal. And you need to consider whether the external drain or the cavity drain is durable when it's exposed to those VOCs and the other contaminants. And think about things like risk to workers during maintenance of pumps. Do you need intrinsically safe pumps? Are the VOCs present at concentrations that can create an explosive atmosphere? Because most of the time we're looking at levels that aren't a risk, but you could be in a situation where maybe it is. So take-home points: VOCs are different to methane and carbon dioxide. You should not rely on membranes alone to provide mitigation in high-risk scenarios. Not all hydrocarbons are VOCs, and so don't require a hydrocarbon membrane. The design process for VOC membranes and other measures requires vapour intrusion risk assessment skills. The design should extend the base risk assessment to show that the mitigation is sufficient. Detailing of the actual system into the construction is different to design. And the risk assessment is not just putting numbers into equations. It needs the right numbers in the right equations and a thorough understanding of contaminated risk assessment. And finally, none of this is new. It's all within Surrey C748, which was published back in 2014. So over 10 years ago now that was published. So there are just a couple of the references. So the NF94 hazardous ground gas got a lot of useful information for methane, carbon dioxide, but also for VOCs, and the Surrey report C749 there. And also there's information on the Clare website as well. So thank you for listening, and I think we've got time for questions now.
Thank you, Steve, for that great presentation. And I love the analogy of the civil structural engineer and the way of, because that's my background as well in civil structural engineering. So, and the analysis is so important in the application of that term now. So those areas where we were talking about. You talked about the understanding of the conceptual modelling, the analysis of that, which then leads on to the design, is a great way. And that applies to us as structural waterproofers as well. So we should follow that process. I was just looking at BS 8102 while you were talking about that. And part of the desk study of BS 812 is also looking at not just the water, potential water ingress into basement structures, but also the other elements as well, such as it says there, hydrocarbons, chlorides, and acids. So that should also take in when considering any form of basement design. So a couple of questions which I can put, was being raised and what have you. So one of the questions is there technology around today that can provide monitoring of hydrocarbons and VOCs without breaking the bank? Or is that based on purely ground investigation reports?
Well, the data that is collected for the design, that you need for the design, is collected during the ground investigations. But there are pieces of equipment that you can buy that allow you. So, for example, if there's a site investigation that's installed monitoring wells, gas monitoring wells or groundwater monitoring wells, and you wanted to go and double check something or get additional information, they're either in situ instruments or you can take the samples. It's a relatively low cost exercise, and you've just got to weigh up the value of doing that versus or the cost of doing that versus what it's going to change in the design. But there are certainly low cost. Well, I say low cost. Depends how you define low cost, I suppose. Like PIDs, for example, photoionization detectors, are probably going to set you back upwards of £7,000 to buy one. So it depends, but you can hire them. A lot of the instruments that we use, if we don't use them that often, then we hire them from hire companies, because they can keep them in calibration all the time, for example, whereas that can be a significant cost if you own it yourself.
So if you're constructing a basement in a known contaminated site and whatever, and we've got a Type C system on that, and we know that the VOCs hydrocarbons will accumulate within the Type C system, is it advantageous to place a monitoring system in that one? In those sort of systems?
Yeah, I mean, you could put permanent monitoring systems in there. That would be a bit more expensive. Or you could do it as part of the validation. So you in ground gas and VOC world, we use a lot of continuous monitoring these days. So you could actually install a continuous monitor in there as part of the verification, probably. I've never done it, but so it's off the top of my head. But I don't see any reason why you wouldn't be able to do that. Or you could, and also you could take. It'd be very easy to take samples of the water that is coming in once it's in there. I mean, it's probably a bit too late, but if you were doing it as a verification exercise again, you could easily take water samples and send them to a laboratory. The cost of testing the samples is not excessive.
Yeah, but that'll then be the case if you have very high rates coming in, or the ground is highly contaminated. I was just looking at your illustration there of a Type C system in a basement, and the amount of VOCs coming into the sumps.
Well, it's not intended to show massive amounts. I mean, it will vary on every site. You've got to assess whether it is a risk or not. Because I mean, there are lots of sites, for example, old petrol stations, where in actual fact the VOC risk is relatively low, and it probably wouldn't be an issue. Whereas go to some dirty gasworks, and the risk is going to be far more significant. Yeah. So you have got to look at it on a site-specific basis.
So this is where the analysis really comes into any particular design which you come up with of a particular membrane, or the application of a membrane. Going back to 748, the model equations, I think they're introduced in that document, aren't they? 748. Yeah, are the model equations for different scenarios, and are they publicly available?
Yeah, I mean,
they're in the document. They're in the document themselves.
Well, they're in the document, but essentially they're basic physics. So what you're looking at is either basic physics or basic chemistry. Right. So you're looking at partitioning equations where if you've got a liquid or a soil concentration, you have to convert that into a vapor concentration in the soil above it. And so there are the things called partitioning equations, which are standard chemical equations. You can find them in any textbook on sort of degree level chemistry. The flow of gas, or VOCs, through the ground is either via pressure-driven flow, which is called advection, in which case you're using something called Darcy's law, which again is a basic principle. It's in numerous textbooks on groundwater flow, or if it's, and the other way that it moves is by diffusion, where if you have an area of high concentration of vapor and low concentration, the difference in concentrations gets you a concentration gradient, and so the vapor just moves from high to low concentration. So that's diffusion, and that uses things called Fick's law, which again is a basic equation that is in numerous textbooks. But in actual fact, recently, the Society for Brownfield Risk Assessment has published an information sheet about how to use those equations. It's directed at ground gas risk assessment, quantitative risk assessment for ground gas, but exactly it applies equally to VOC risk assessment as well. So you've got to just take those basic building blocks, and then you've got to look at what the likely pathways are into your building, or look at what the permeation rates are through the membrane, and apply them to those different scenarios.
Lovely. Thank you for that. Yeah, so basic physical and chemical principles applied throughout the whole industry. Then, yeah, brilliant. Just one more. In terms of the membranes, what is the main difference between a membrane specification that handles methane as opposed to a VOC? Is there any differences?
No, I mean there are different. Most of the differences that occur because of sales and marketing practices.
Right.
So, for example, we quite often in gas protection world will use an HDPE membrane that is thick, because we know that is more durable and it's more resistant to damage. But it's got a methane permeation rate that exceeds the value, the guidance value in BS 8485. But as designers, we have to make a decision as to which is the safest solution.
Right.
So, and the same thing applies with VOC membranes. There are some materials that I could go tomorrow and use as a VOC membrane in theory, but I would have to spend the money to get the permeation test data, because the people that are selling it are not selling it as a VOC membrane, and they've not spent the money to do the VOC permeation test. So that information is not on their data sheets. So I suppose the key difference is, have you got the data? Have you got the permeation data to allow you to design it? And that is the most important thing.
And as you've rightly pointed out, as a designer, we have that duty of care to make sure we're applying the right things at the right time. Yeah,
without
that
doubt,
duty of care principle.
Yeah, I mean, I had quite a long discussion with a lawyer about this, about just accepting what is written on data sheets, and they said that as a designer, you've got a duty to make sure that is, if there are glaring obvious mistakes in it, and you should be competent enough to see that. If you don't question it, you'll be in trouble.
And as one structural engineer for another one, if you don't ask you've got to ask the question, haven't you?
Yeah.
If in doubt, ask.
Yeah.
Yeah. Get it right. Lovely. Thank you very much, Steve.
That's okay.
For your presentation, and some of the questions as well. Response to them. That's brilliant. So we look forward to the next webinar, which I haven't got any details of this particular time, but watch your space, and the PCA will be presenting another webinar next month. So thank you very much for your time, and thank you for all attending this webinar on hydrocarbons and VOCs. Thank you very much.
Thank you.
Thank you.